Hello and welcome back to Introductory Astronomy. Today we're going to start talking about stellar evolution, the life and death of a star. After reaching the main sequence, a newborn star changes little in outward appearance for more than 90% of its lifetime. However, at the end of that period, as the star begins to run out of fuel and die, its properties once again change drastically. Aging stars travel along evolutionary tracks that take them far from the main sequence as they end their lives. In this and the next two chapters, we will study the evolution of stars during and after their main sequence burning stages. We will see that the ultimate fate of a star depends primarily on its mass, and that the final states of stars can be very bizarre. By continually comparing theoretical calculations with detailed observations of stars and binaries of all types, we're able to refine the theory of stellar evolution into a precise and powerful tool for understanding the universe. In this opening picture right here, we see what is called a planetary nebula. A planetary nebula, unlike what the name implies, has nothing to do with planets. It is the ejected envelope of a red giant star spread out over a large volume. In this picture right here, it's a popular planetary nebula known informally as the cat's eye, or more formally as NGC 6543. This picture is a composite image of visible light acquired by the Hubble Space Telescope and X-ray radiation acquired by the Chandra Telescope. In terms of dimensions, this is a very large planetary nebula that spans over light years. In this chapter, we're going to cover leaving the main sequence, how do stars like the Sun evolve, the death of a low-mass star and a high-mass star, how we can observe stellar evolution within star clusters, and binary star systems. And we're going to start with leaving the main sequence. Of course, we cannot observe a single star going through its whole life cycle, because the life cycle of a star is anywhere between millions to trillions of years, and we don't live that long to make those observations. So how do we get around that? We make observations of stars in star clusters. This is a very powerful tool because it helps us construct a complete picture of all the stages of a star's evolution. We know that during the stay of a star on the main sequence, the star is in equilibrium. But eventually, the hydrogen in its core is going to be consumed, fused into helium, and the star will begin to leave the main sequence. Its evolution from then on depends very much on the mass of the star. Low-mass stars go quietly, and high-mass stars go out with a bang. Let's take a look at stars that are similar to our Sun. Even while on the main sequence, the composition of a star's core is changing as it fuses hydrogen into helium. In the graph on the slide, we see hydrogen represented in yellow and helium in blue, and the graph shows the abundances of the two. In frame A, we have the abundances at birth, just as the star arrives on the zero-age main sequence, or the ZAMS. In frame B, we see the abundances after 5 billion years. At this stage, only a few % of the star's total mass has been converted from hydrogen into helium. This change speeds up as the nuclear burning rate increases with time. And notice how within the core, the abundances have drastically changed. It's about half and half of hydrogen and helium. And if you take a look at frame C, we see the abundances after about 10 billion years, which is the amount of time a sun-like star stays on the main sequence. As the fuel in the core is used up, the core begins to contract. When it is totally used up, the core will start to collapse. Hydrogen begins to fuse outside the core. So if you take a look at the picture over here, you see hydrogen shell burning. So as the star's core converts more and more of its hydrogen into helium, the hydrogen in the shell surrounding the non-burning helium burns even more violently. By the time shown here, which is little after stage 8 in table 20.1, the core has shrunk to a few tens of thousands of kilometers in diameter, whereas the star's photosphere is 10 times the star's original size. So if we take a look at the table here representing the stages of a star leaving the main sequence, stage 7 is right on the main sequence. It's about 10 billion years, with a central temperature of 15 million Kelvin and a surface temperature of 6,000 Kelvin. Notice how its radius is 1 solar radii. As we move on to stage 8, the central temperature is starting to increase. It increases to 50 million Kelvin, and the surface temperature is decreasing. As this is taking place, the star itself gets larger and larger, and it gets to about 3 solar radii. We now say that our star has moved on to the subgiant branch. This is a very nice summary of all the stages as a star leaves the main sequence. So you can read through those, pay attention to how long a star stays on each stage, and how its temperature and its radius are changing. Stage 9 is an important stage, and that is when we say that the star is in the red giant branch. The star has now heated up its core to about 100 million Kelvin, and its surface temperature has dropped to about 4,000, but it has swelled up to about 100 times its solar radius. So it has become very large, a giant. As the core continues to shrink, the outer layers of the star expand and cool, which is why its surface temperature drops. In terms of our sun, it would extend as far as the orbit of Mercury. So it would swell up that much when it becomes a red giant. Now, despite its cooler temperature, its luminosity increases enormously because its size has increased a lot. So even though its surface temperature is cooler, the star itself is so much bigger that its overall luminosity is a lot more than it was before. Here is the red giant stage represented on the HR diagram. As the helium core shrinks and the outer envelope expands, the star leaves the main sequence. Stage 7 over there. At stage 8, the star is well on its way to becoming a red giant. The star continues to brighten and grow as it ascends the red giant branch to stage 9. And you can see how the diagonal dashed lines that represents the radius of the stars are also increasing. So we got to the point where it's 100 times the radius that it had to begin with. Stage 10 is what we call the helium fusion. Once the core temperature has risen to 100 million Kelvin, the helium in the core starts to fuse through the triple alpha process. So you can see there two helium atoms are fusing together to give beryllium-8 and some energy. That beryllium-8 then in turn fuses with helium-4, and we get out carbon-12 plus some energy. The reason that happens is because beryllium-8 is highly unstable, and it will decay within about 10 to the minus 12 seconds. That is why high temperatures and densities are necessary in order to get carbon at the core of a star. The helium flash. The pressure within the helium core is almost totally due to what we call electron degeneracy. Electron degeneracy is when two electrons cannot be in the same quantum state. So this tells you that the core cannot contract beyond a certain point. This pressure is almost independent of temperature. When the helium starts fusing, the pressure cannot adjust. Helium begins to fuse extremely rapidly. Within hours, the enormous energy output is over, and the star once again reaches equilibrium. So a large increase in luminosity occurs as the star ascends the red giant branch, ending in the helium flash that you see there on stage 9. The star then settles down into another equilibrium state at stage 10, which we call the horizontal branch. Stage 11. Back to the giant branch. As the helium in the core fuses to carbon, the core becomes hotter and hotter, and the helium burns faster and faster. The star is now similar to its condition just as it left the main sequence, except now there are two shells. There is the non-burning envelope, followed by the hydrogen-burning shell, followed by the helium-burning shell, and in the very center, the carbon ash that's left over. This takes place within a few million years after the onset of helium burning in stage 9, and carbon ash starts to accumulate in the star's inner core. And as you can see in this picture, above the core, hydrogen and helium are still burning in concentric shells. The star has become a red giant for the second time. In the HR diagram, you see how we have the reascension to the red giant branch. A carbon core star re-enters the giant region of the HR diagram, this time on a track called the asymptotic giant branch, which is represented by stage 11. And that it goes there for the same reason it evolved the first time around. Lack of nuclear fusion at the center causes the core to contract and the overlying layers to expand. So that's what takes place with stars that have mass similar to the Sun. What happens to stars that have mass less than the mass of the star? Well, if you take a look at this graphic that here, it shows the entire evolution of a Sun-like star. So if you start from stage 4 over there, protostar, stage 7 represents the main sequence G-type star. Continuing on to stage 8 and follow the arrows, go right to stage 9, so we have the red giant, and eventually down to a white dwarf. Now, stars like that never become hot enough for fusion past carbon to take place. There is no more outward fusion pressure being generated in the core, which continues to contract. As a result, the outer layers become unstable and are eventually ejected. This is a graph showing the red giant instability buffeted by helium shell flashes from within and subject to the destabilizing influence of recombination. The outer layers of a red giant become unstable and enter into a series of growing pulsations. Eventually, the envelope is ejected and forms a planetary nebula, like you saw in the opening slide. The ejected envelope expands into interstellar space, forming this planetary nebula, and the pictures showing in frame A is Abell 39 nebula, which is about 1.5 parsecs across. This is a classic planetary nebula, and it's shedding out a spherical shell, and you can see what was responsible for that right at the location of the arrow. Frame B is the brightened appearance around the edge of Abell 39, and this brightened appearance is caused by the thinness of the shell of glowing gas around the central core. Very little gas exists along the line of sight between the observer and the central star along path A, so that that part of the shell is invisible. Near the edge of the shell, more gas exists along the line of sight, paths B and C, so the observer sees a glowing ring. And frame C shows the Ring Nebula, a very famous planetary nebula, which is about 1,500 parsecs away and is half a parsec across. It is too small and dim to see with the naked eye. We used to think that its appearance could be explained in much the same way as that of Abell 39. However, it now seems that the ring really is ring-shaped. Researchers are still unsure as to why a spherical star should eject a ring of material during its final days. So at this stage, the star has two parts: a small, extremely dense carbon core and an envelope about the size of our solar system or larger, enveloping the core. And this is just a reminder that a planetary nebula has nothing to do with planets. But we used to think, when we looked at that it resembled a planetary system, so it was labeled planetary nebula, and that name remained. Now, planetary nebula can have many shapes. In frame A, you see what's called the Eskimo Nebula. It clearly shows several bubbles or shells of material being blown into space, and it resides about 1,500 parsecs away in the direction of the constellation Gemini. Frame B shows the Cat's Eye Nebula, about 1,000 parsecs away and 0.1 parsecs across. It is an example of a much more complex planetary nebula, and it was possibly produced by a pair of binary stars that have both shed envelopes. Frame C shows M29, which is about 600 parsecs away and half a parsec end-to-end. As you can see, there are two lobes or twin jets of glowing gas emanating from a central dying star. And those jets of gas are racing out at speeds of about 300 kilometers per second. So as the dead core of the star continues to cool, the nebula, the envelope of material that it expanded, continues to dissipate and expand in the surroundings. Stages 13 and 14 represent the white and black dwarf stage. Once the nebula is gone, the remaining core is extremely dense and extremely hot, but very, very small. It is now luminous only due to its high temperature. Remember, it's done fusing anything, so we can still see it because it's very, very hot. A star passage from the horizontal branch at stage 10 to the white dwarf stage, which is stage 13, is represented on the HR diagram. And notice how it's doing that by way of the asymptotic giant branch, and it creates an evolutionary path that cuts across the entire HR diagram. So follow the arrows from stage 10 to 11, 12 to 13, and you see how it follows this interesting evolutionary path. Here's an example of the small star Sirius B, which is a companion of the much larger and brighter Sirius A. Sirius B is a white dwarf, and it's represented by the dot on the right on the slide. The spikes on the image that you see of Sirius A are not real. They're caused by the support struts of the telescope. The Hubble Space Telescope has detected white dwarf stars in globular clusters. In frame A here, you see the globular cluster M4. It's about 1700 parsecs away, and it spans about 16 parsecs. In frame B, we will have a peek at M4 suburbs by the Hubble Space Telescope, and we can clearly see 100 white dwarfs within a small 0.2 square parsec region. Now, as a white dwarf cools, its size does not change significantly. It simply gets dimmer and dimmer and dimmer until it finally ceases to glow. Once it ceases to glow, we call the white dwarf black dwarf. This is an outline of stellar formation and extinction of the globular cluster M80. What is called the blue stragglers, and you can see in the HR diagram on frame B, it's stars that appear to have been left behind. But they're not exceptions to the stage evolutionary path we just described. They are stars that have formed much more recently, probably from the merger of smaller stars, which is why they don't follow the evolutionary path just described. In frame A is just a picture of the globular cluster M80, and it's about 8,000 parsecs away. Let's take a look at the HR diagram a little bit more closely. This data that you see there in frame B is based on ground and space observation, and that's from several globular clusters, similar in overall composition to M80 in frame A. You can see clearly the various evolutionary stages predicted by theory and shown schematically in figure 20.11 in the textbook. Now again, these blue stragglers are main sequence stars that appear to have been left behind as other stars evolved into giants. The current best theory is that they're the result of merging binary systems or even collisions between stars of lower mass in this remarkably dense stellar system. So if a globular cluster is very dense, it's not unlikely for actual star collisions to take place. The little inset on the bottom right shows the HR diagram of another globular cluster, NGC 2808. And it reveals that the main sequence is actually made up of 3 distinct sequences, increasing in helium content from right to left, and suggesting multiple generations of star formation shortly after the cluster has formed. Learning astronomy from history. Now, Sirius is the brightest star in the northern sky, so it has been recorded throughout history. So we have a lot of data on this particular star. However, there is a mystery. all sightings recorded about between 100 BC and 200 AC describe it as being red, but now it looks blue-white. So the question is why? What happened? So one solution to the problem would be perhaps there was an intervening dust cloud that was changing the color that we see. But if that's the case, where has it gone to? Well, what if instead it had a companion, and its companion was a red giant, which is why they were able to see it as reddish? Then if that's the case, then it became a white dwarf very quickly. So that's one of the mysteries in astronomy, is the color of Sirius. So if you want to read details on that, take a look at your textbook in Discovery section 21. So we just covered sections 20.1 through 20.3. You should be able to outline the events that occur as a sun-like star evolves from the main sequence to the giant branch, explain how the sun will eventually come to fuse helium in its core, and describe what happens when that occurs, and be able to summarize the stages in the death of a typical low-mass star and describe the resulting remnant.